Welcome again to today's webinar, The Critical Role of Thermal Modeling for Battery Safety and Performance. Thermal modeling is a cornerstone for ensuring the safety and performance of lithium-ion battery systems, particularly in applications like electric vehicles and grid-scale energy storage. Effective thermal management not only prevents issues like thermal runaway, but also significantly enhances battery lifespan and reliability. In this session, I will share from my research at the UFA or the University of Arizona, focusing on advanced electrochemical thermal models. These models predict and mitigate thermal failures like thermal runaway by simulating heat generation, dissipation, and failure propagation, key to enhancing safety and driving design improvements. We'll also introduce Ridgetop Group's battery diagnostic and prognostic system, the BDPS tool suite. This tool suite is evolving to include advanced thermal management and modeling capabilities, enabling the battery R&D community to better address safety and performance challenges. By the end of the webinar, you'll gain actionable insights into advanced thermal modeling techniques, strategies to prevent thermal runaway, and innovative tools for battery diagnostics and safety. Together, let's explore how these advancements pave the way for a safer, more efficient, and sustainable energy future. This slide outlines the agenda for today's presentation. We'll begin with an introduction to Ridgetop Group and our collaboration with Idaho National Lab, followed by a shout out to the University of Arizona's contribution in my research work. Next, we'll dive into the background of our research and the problem description and motivation that sets the stage for our work. From there, we'll explore our modeling methodology and present key results and discussions that highlight the impact of our approach. We'll then introduce the BDPS tool suite, a cornerstone of our work at Ridgetop, and discuss potential future work and collaboration opportunities. Finally, we'll wrap up with a summary of our findings before opening the floor to questions and sharing our contact information for further discussions. Ridgetop Group has a long-standing partnership with Idaho National Lab, a collaboration that has spanned nearly a decade. INL, part of the U.S. Department of Energy's National Lab Network, is located in Idaho Falls and is renowned as one of the nation's top research labs for lithium-ion battery advancements and clean energy technologies. INL is also a national leader in nuclear energy research, further showcasing its broad impact on energy innovation. At Ridgetop Group, we are recognized leaders in developing hardware, firmware, and software solutions for condition-based maintenance, prognostic health management, and reliability engineering. Our mission is to enhance safety, efficiency, and operational performance for government and commercial applications, all while reducing maintenance and sustainment costs through innovative technology. With over 20 years of experience, we continue to set benchmarks in reliability and health management solutions. We are proud to be an AS 9100D and ISO 9001 certified facility, underscoring our commitment to quality and excellence in everything we do. Here's a small shout out to the Department of AME, the Aerospace and Mechanical Engineering at the University of Arizona, where I did my PhD. At our lab, we do a study of rechargeable batteries, whether through numerical simulations or machine learning. Even we do a lot of experimental measurements. Our group also offers courses for undergraduate and graduate students in mechanical engineering as well. So thanks to my advisor, Dr. Yurkiv, and also to the university for the research work that I did there. Lithium-ion batteries are central to modern technology, powering portable electronics, electric vehicles, and renewable energy storage systems. Their widespread adoption is driven by key advantages, including high energy density, high efficiency, and versatility in scaling for different applications. With a global push towards renewable energy and electric mobility, lithium-ion batteries usage has surged significantly. However, alongside these benefits Concerns about battery safety and lifespan persist, as highlighted by incidents of thermal runaway and related failures. These challenges underscore the need for ongoing research and innovation to ensure uh, uh, for incidents of thermal runaway and related failures. These challenges underscore the need for ongoing research and innovation to ensure the safe, reliable, and sustainable use of lithium-ion batteries in the future. Thermal runaway is a critical issue in lithium-ion batteries caused by rapid heat generation from exothermic electrochemical reactions, mechanical abuse, or thermal abuse. Once initiated, thermal runaway can escalate uncontrollably, leading to catastrophic failures that not only damage the battery but also endanger consumer safety and lives. Examples of such events or incidents are illustrated here, showing the severe consequences of thermal runaway in vehicles and electronic devices. Experimentally monitoring thermal runaway is highly challenging due to its rapid progression and the extreme conditions it creates. Traditional methods often fail to capture the intricacies of thermal events in real time, highlighting the need for predictive and preventive solutions. These challenges bring us to the question, can AI-driven or machine learning be leveraged to predict thermal runaway using results from multiphysics-based models? Such an approach could revolutionize battery safety by enabling proactive monitoring and response strategies, potentially preventing life-threatening disasters and ensuring reliable battery performance. This slide sets the stage for exploring how advanced modeling and AI can address this pressing issue. This slide presents an overview of the workflow mechanism adopted in our study. The process begins with multiphysics modeling of lithium-ion batteries, where we simulate their behavior under various conditions. Importantly, we introduce degradation mechanisms such as side reactions into these models to replicate real-world scenarios that lead to thermal anomalies. Using these models, we perform numerous simulations to generate a large data set. These results capture the temperature distribution within the battery under different operating conditions, forming the foundation of our machine learning study. The next step involves feeding these results into a deep learning network. The network consists of multiple layers, each designed to extract specific features from the data. These extracted features allow the network to classify different battery operational states, enabling us to predict conditions such as normal operations, degradation onset, or thermal runaway risks. This workflow illustrates the integration of advanced modeling with machine learning, creating a powerful framework for understanding and predicting battery behavior under complex conditions. On this slide, we highlight the integration of two crucial components of modeling lithium-ion battery performance. The cell model, specifically the P2D model or the pseudo 2D model, also known as the Doyle-Fuller-Newman model, the DFN model, and then the thermal model, which operates in 3 dimensions. Together, these form a robust multiphysics framework that captures the electrochemical and thermal dynamics of battery systems. The P2D model depicts on the left provides a detailed representation of the electrochemical processes within the battery. It includes the transport of lithium ions in the electrolyte and within the electrodes, governing equations for charge and mass conservation, the coupling of solid phase diffusion in the anode and the cathode with the electrolyte dynamics. This model is key to understanding charge discharge behavior and predicting localized states like depletion within electrodes. On the right, we have the thermal model, which works in 3 dimensions to account for temperature distribution and heat transfer in the battery and its surrounding. The thermal model incorporates heat generation from the electrochemical reactions and resistive heating in the cell, heat dissipation through the cell's surface, and cooling mechanisms such as airflow or thermal management systems. The mesh diagram here illustrates the resolution of temperature gradients and hotspots, providing insights into thermal safety and efficiency. These two models are connected by the generated heat source. The P2D model calculates heat generation as a result of electrochemical reactions, which is then fed into the thermal model to simulate how heat spread spreads within the cell and its environment. The interaction is vital for understanding thermal runaway risks and designing effective cooling strategies. Let's talk briefly about the P2D model. The P2D model is one of the most widely used frameworks for simulating lithium-ion batteries. It strikes a balance between computational efficiency and detailed electrochemical insights, making it a cornerstone for battery research and development. The P2D model divides the battery into two primary phases, the electrolyte and the solid phase. The electrolyte phase tracks ion concentrations and potential, while the solid phase models lithium-ion diffusion within the electrode particles. These phases are interconnected through equations for charge conservation, ensuring accurate current distribution across the cell. And also to be noted that as these two phases exist in continuum, since it's based on the porous electrode theory, which specifies that the electrode and the electrolyte exist together in the electrode. The solid phase and the electrolyte phase exist together in the electrode. One of the strengths of the P2D model is its ability to simulate charge-discharge profiles under various conditions, providing insights into parameters like state of charge and state of health. It also allows us to analyze how thermal and mechanical stresses interact with the electrochemical performance. This makes it invaluable for optimizing battery designs, developing advanced charging protocols, and conducting safety analysis to prevent events like thermal runaway. Looking ahead, we aim to integrate the P2D model with advanced thermal and aging models to create a holistic simulation framework. By coupling it with real-world performance data, we can make even more precise predictions about battery behavior in practical applications. This will pave the way for safer, more efficient, and longer-lasting energy storage systems. The solid electrolyte interface. uh, let's discuss what the solid electrolyte interface is, because since we have considered it in our model, and it also leads to aging of batteries. But before going into more details, let's understand briefly what it is. So the SEI is a crucial component of lithium-ion batteries, formed as a thin layer on the surface of the anode during the initial cycling process. This film consists of various inorganic and organic lithium compounds and acts as a protective layer, preventing further electrolyte breakdown and stabilizing the battery during operation. While the SEI is beneficial, providing stability and enhancing the battery's lifespan, it also prevents a critical challenge. During discharge, the SEI can decompose, releasing significant amount of heat. This decomposition becomes a key factor in thermal events, particularly under conditions of high stress or failure. In this research, SEI decomposition has been assumed as the primary trigger for exothermic heat release. This heat generation, if unchecked, can escalate into thermal runaway once chain reactions start to occur. A dangerous phenomena where the battery's temperature rises uncontrollably, potentially leading to catastrophic failure. Understanding and modeling SEI behavior is therefore essential to predicting and preventing such events. Now that we have covered the electrochemical aspects using the P2D model, let's dive into the thermal model, which addresses another critical dimension of battery performance, the temperature management. Thermal modeling ensures that batteries operate safely and efficiently under various conditions. The primary goal of thermal modeling is to ensure stability by identifying hotspots and designing optimal cooling strategies. Temperature regulation is essential to prevent issues like uneven aging, reduced efficiency, or in the worst case scenario, thermal runaway. The thermal model has three main components: heat generation from electrochemical reactions with resistive losses, heat transfer mechanisms including conduction within the cell and convection with the surrounding environment, boundary conditions such as airflow and ambient temperature, which simulate real world scenarios like operating in a hot climate or under heavy load. The model uses 3D finite element analysis, which provides detailed spatial resolution of temperature gradients across the cell. It's tightly integrated with the electrochemical model to use realistic heat generation data. Additionally, it considers critical material properties such as thermal conductivity and heat capacity to ensure accurate predictions. This model plays a pivotal role in designing effective cooling systems, whether for EVs or stationary storage systems, predicting and mitigating thermal runaway risks by identifying high temperature regions, validating battery performance under extreme conditions such as rapid charging or very high ambient temperatures. This slide showcases the fundamental process of charging and discharging in a lithium-ion battery, illustrated through the voltage profiles and schematic representations of ion movement across the cell. Batteries are characterized by their charge and discharge cycle. Let me explain the two processes. Discharge. During discharge, lithium ions move from the negative electrode to the positive electrode through the electrolyte. This generates an electric current that powers external devices, as shown in the voltage profile in the top curve. During charging, the process is reversed. Lithium ions migrate from the positive electrode back to the negative electrode, as seen in the bottom curve. Looking at the voltage curves, on the x-axis we have time in seconds, on the y-axis the cell voltage in volts. The repetitive charge and discharge cycle demonstrates the battery's ability to store and release energy. The schematic on the right provides a closer look at the internal structure of the battery. The negative electrode, typically graphite, is on the left, and the positive electrode commonly could be NCA, NMC, LFP, or there are many more alternatives shown on the right. Lithium ions travel through the separator in the electrolyte during charge and discharge, completing the circuit. These arrows indicate the direction of ion movement during each process. The cycling of lithium-ion batteries, lithium ions performs the basis of battery operation. By analyzing these charge discharge curves, we can determine key characteristics such as capacity, efficiency, and cycle life. Now let's talk briefly about the results. Here in this slide, we present the results, particularly the multiphysics modeling results on the effect of SEI decomposition on battery behavior with a focus on thermal runaway risk. Here we compare the results for cases involving a single hotspot and multiple hotspots within the battery. Additionally, we visualize the temperature contours of the cell to better understand heat propagation. Let's start by examining the graphs and visualization. On the left, we see charge discharge profiles for two cases. Over time, these cycles demonstrate capacity fading due to SEI growth. And also we show decomposition by the reduction in the SEI thickness shown by the green curve, which accelerates as the system becomes unstable. In the middle, the green curve, as I mentioned, shows the SEI thickness growth, while the red curve shows the corresponding temperature rise, to be precise, the maximum temperature rise. Notice how SEI decomposition leads to rapid self-heating, particularly in the case with multiple hotspots. The 3D temperature contour on the right visually highlights the hotspots. The model with two hotspots reaches thermal runaway faster due to greater localized heat release within a short time frame. This comparison highlights the role of multiple hotspots in accelerating thermal runaway. With two hotspots, the localized heat generation is higher and propagates faster, leading to a rapid rise in temperature. This underscores the importance of controlling hotspot formation and distribution within the cell to enhance safety. We conducted simulations by varying both the location and the number of hotspots within the battery. This provides a comprehensive data set that can now be used for machine learning studies. By leveraging this data set, we aim to predict thermal runaway scenarios and identify critical conditions that trigger instability, offering actionable insights for battery safety design. This slide presents a visual representation of the temperature distribution within the lithium-ion battery under two scenarios, a single hotspot and two hotspots. It also illustrates the impact of airflow on the cooling process and how the temperature variations influence thermal runaway initiation. For the single hotspot case on the left, we see the temperature contour and the air flow lines demonstrate the cooling effect. But as shown in the slide cross section, the maximum temperature is concentrated at the hotspot. This is where the thermal runaway propagation begins. This localized heating is critical as it drives the initiation of thermal runaway. And for the two hotspots case on the right, we observe the scenario that the temperature contour highlights multiple zones of elevated temperature. The increased heat release from the two hotspots accelerate the rise in temperature and reduces the time to thermal runaway compared to the single hotspot's case. The arrows represent the cooling airflow distribution around the battery. While airflow can moderate the overall temperature, it cannot entirely counteract the localized heating caused by hotspots. This is evident from the persistence of maximum temperature at hotspot locations. By comparing the two cases, we see that multiple hotspots not only elevate the overall temperature but also intensify the thermal instability within the battery. This highlights the importance of precise hotspot management and robust cooling strategies to delay or prevent thermal runaway. This slide demonstrates how we extend our single cell model to represent a battery module. By building on the foundations of the single cell model that we presented earlier, we scaled up to simulate interactions and thermal behavior at the module level, which is crucial towards understanding real world battery performance. On the left, we have the single cell model, which provides a detailed understanding of the thermal and electrochemical behavior of an individual cell. This model includes cylindrical cell enclosed within an air compartment, cooling airflow applied to regular temperature. These foundational insights serve as the basis for module level modeling. Moving to the right, you can see a battery model representative unit. Since modeling an entire battery module with dozens or even hundreds of cells is computationally intensive, we choose to model a representative unit consisting of 4 cells. This approach balances computational efficiency with capturing the key thermal and electrochemical interactions between cells. The geometry for this model was designed in SolidWorks and includes essential cooling elements like the cooling snake. The 4 cells labeled B1 to B4 allows us to study heat transfer and dissipation within the module, analyze the effectiveness of cooling strategies, and evaluate interactions between the cells that contribute to thermal runaway or performance degradation. At the bottom, you can see how this representative unit connects to the real-world applications such as electric vehicle battery packs. By understanding the thermal behavior at this intermediate scale, we can improve the design of cooling systems and optimize the layout of battery modules within the pack. However, at this point, we are only focusing mostly on predicting thermal failure in modules or in general in electric vehicles. This slide presents the multi-physics modeling approach for a representative battery module containing 4 cells from a typical electric vehicle battery module. This model integrates the thermal model and material interactions within the module to simulate real-world operating conditions. The battery module model includes several key elements. The 4 cells are arranged along with the cooling snake assembly, which is inserted in a protective case. The cooling fluid is usually 50% ethylene glycol and water mixture. The voids within the cases are filled with polymeric material, which helps stabilize the cells and improve thermal conduction. And as I mentioned, cooling is achieved using water glycol mixture that flows through the cooling snake, effectively dissipating heat generated by the cells. The model employs an unstructured quadratic finite element mesh for the simulation. This mesh type ensures high accuracy in capturing the complex thermal and fluid interactions, especially around the cells and within the cooling assembly. In this study, we consider both single and multiple hotspots at various locations within the module. These hotspots are critical as they lead to localized temperature rise, which can escalate into thermal runaway in one or more cells. By varying hotspot locations, we generate a comprehensive data set of uh, thermal temperature distribution for machine learning applications, enabling predictive modeling of thermal behavior and risk assessment. This multi-physics model allows us to simulate the thermal performance of the module under different cooling conditions, evaluate the effectiveness of the water glycol cooling systems in managing heat dissipation, and also generate data to train machine learning models for identifying high-risk thermal scenarios. This slide presents the results of the constant charge and discharge cycles and highlights the effect of SEI decomposition on the battery's thermal behavior. These findings are crucial for understanding capacity fade and thermal runaway in lithium-ion batteries. On the left, we see the charge-discharge curves for multiple cycles. Over time, we observe capacity fading due to the growth of the ACI layer on the anode. This layer forms during cycling and consumes active lithium, reducing the battery's capacity. The fading trends are evident as the charge discharge cycles or profiles decrease in amplitude with each cycle. And just to note that we have considered the degradation of battery mostly in battery B2, that is shown in red color, and that's why we see more capacity fading in battery B2 compared to the other ones. On the right hand side, we focus on the temperature behavior of the cells within the module. The ACI decomposition and exothermic reaction plays a critical role here. As the ACI breaks down, it releases heat, leading to self-heating of the battery. This accumulates over cycles, causing an exponential temperature increase as shown in the Tmax, or the maximum temperature versus time plot. The temperature rise accelerates over time due to exponential dependence described by the Arrhenius equation. This relationship indicates that as the temperature increases, the rate of the decomposition rises exponentially, and also it rises the rate of the heat release term, further fueling the rise in temperature. And eventually, this cycle of self-heating leads to thermal runaway, a catastrophic failure mode for batteries. The inset image illustrates the arrangement of cells B1, B2, B3, B4 in the module. This slide demonstrates how we incorporated real-world driving cycle data as an input to our battery model. Using driving patterns allows us to simulate the battery's performance under practical conditions, bridging the gap between laboratory tests and real-world applications. On the right, we see the FTP75 driving cycle, or the Federal Test Procedure 75, which is a standard test procedure developed by the EPA. This cycle represents urban driving conditions, including periods of acceleration, deceleration, cruising, and idling. The speed profile fluctuates over time, reflecting typical stop and go traffic behavior encountered in city driving. We use this dynamic cycle as an input for our battery model to simulate the dynamic current demand on the battery, the thermal effects, the capacity fade, and of course the voltage characteristics. By incorporating driving cycle data, our model can predict how the battery will behave in an actual electric vehicle, taking into account varying speed and load conditions. This approach helps us evaluate the impact of driving patterns on battery life and efficiency, identify thermal and performance bottlenecks, and also it can help us to develop efficient or optimized battery management strategies tailored to specific driving scenarios. This slide demonstrates the results of simulations that use real-world driving cycle data to study the performance and thermal behavior of lithium-ion batteries. By applying driving cycles, we can access how the dynamic load affects charge-discharge behavior, the SEI growth, and risk of thermal runaway. On the left, we see the charge-discharge curves for 4 cells, B1 through B4 over the simulated driving cycle. The curve clearly shows capacity fading due to SEI growth, specifically in battery B2, since that's our main faulty battery. We also see that the voltage profiles gradually decrease with showing capacity fading, particularly in B2 compared to the other batteries. And also different cells experience varying levels of capacity fading, while B2 showing the most significant degradation. On the right, we observe the temperature behavior of the cells during the simulation. Gradual heating, initially all cells add heat up gradually due to normal operation. But as the SEI decomposition that's mostly prominent in our faulty battery B2, it accelerates self-heating especially, which exhibits a sharp rise in temperature. The red curve for B2 shows an exponential temperature increase, which is characteristic of thermal runaway. This behavior aligns with the Arrhenius equation, which explains the exponential dependency of reaction rates on temperature. These results highlight the non-uniform degradation and thermal behavior among cells, emphasizing the need for monitoring and balancing mechanisms in battery packs, and also the crucial role of SEI decomposition in triggering thermal runaway, especially under realistic driving conditions. In summary, driving cycle informed simulations provide a realistic understanding of battery performance and thermal safety. These findings are instrumental in designing robust battery management systems to mitigate risks and informing and improve the safety and longevity of EV batteries. This slide presents temperature contour plots for a battery pack model showcasing the effects of varying hotspot location within the battery. These simulations are critical for understanding thermal behavior and generating data for machine learning applications. On the left and right, we see the temperature contour for two scenarios with different hotspot locations. The color scale indicates the temperature distribution, with hotter regions represented in yellow and cooler regions in red. These visualizations clearly show how the placement of hotspot influences the heat distribution across the battery cells and the surrounding cooling medium. The variations in hotspot location serves dual purpose. It helps us understand the thermal impact of different failure points within the battery pack. More importantly, it allows us to generate a larger and more diverse data set for training machine learning model. A larger data set improves the accuracy and generalization, also the robustness of predictions, enabling better insights into thermal runaway risks and hotspot management. By varying hotspot locations, we can evaluate how specific cells or regions within the battery pack results respond to localized heating and the effectiveness of cooling strategies in mitigating temperature spikes. This slide poses a crucial question: how can we leverage the results of our simulation and experiments for machine learning? The data we have generated so far through modeling and simulation offer a wealth of information that can be transformed into actionable insights with the help of machine learning. In summary, the results we have obtained through modeling and simulation are just not static findings. These are foundations for developing predictive models that enhance safety, efficiency, and performance in modern battery systems. This integration of modeling and AI is a game changer for the energy storage industry. Let's see how we can address this question. This slide introduces the concept of spatiotemporal machine learning as a framework for predicting future behaviors, analyzing both spatial and temporal data. The example shown here utilizes the state of Arizona to demonstrate how data points representing locations across the state can be analyzed over time to build predictive models. On the left, you see a map of Arizona with multiple locations marked. These points represent spatial data such as position of vehicles, and their connection illustrate the relationship or paths between them. When combined with temporal data such as speed at each location, we create a graph structured dataset that evolves with time. The middle section illustrates how this data is structured for machine learning. Each graph layer corresponds to a snapshot in time, capturing the dynamic interactions between spatial points. These graphs form the input to our deep learning models, which are specifically designed to handle spatiotemporal dependencies. By incorporating both spatial relationships and temporal trends, The models can learn specific or complex patterns that are not apparent in static datasets. Excuse me. Finally, on the right, we see the outcome of the deep learning process, prediction of future states. In this case, the model could predict the speed or behavior of the system at future time intervals based on historical spatio-temporal data. This approach is highly relevant for applications like traffic forecasting, dynamic energy optimization, or real-time monitoring of distributed systems. In summary, spatio-temporal machine learning bridges the gap between historical data and future predictions by capturing the interplay between space and time. This methodology is especially powerful for systems like electric vehicles, where understanding how spatial behaviors evolve over time can lead to more efficient designs and improved performance. Building on the foundation of spatial temporal machine learning concepts from the previous slide, this slide focuses on how we prepare the dataset for machine learning tasks using temperature data from our simulation. Specifically, we address a time series prediction problem where the goal is to forecast future temperature distribution based on historical observations. The figure on the left represents the battery geometry where the temperature variations are simulated. The red line spiraling along the surface of the battery illustrates the temperature sensor's path, which captures the temperature measurements at spatially distributed points over time. This spatial variation in temperature along the thermocouple is crucial for understanding the behavior of the battery under dynamic conditions. To integrate simulation results with machine learning workflow, we utilize the LiveLink for MATLAB interface. This powerful bidirectional tool enabled us to extract temperature data from the simulations and transfer it to MATLAB, where the data could be further processed. Specifically, temperature values were recorded at specific spatial coordinates along the thermocouple for each time step during the battery's operation. These extracted datasets stored as CSV files capture both the spatial and temporal evolution of temperature. However, the raw simulation data in CSV format is not directly suitable for input into machine learning models. To address this, we needed to restructure the data into graph-based format. This process involved mapping the spatial coordinates of the thermocouple or the thermal sensor onto a graph structure where each node represents the measurement point and the edges represent pairwise spatial relationship. In this representation, temperature at any time is conceptualized as a graph signal where the temperature values at the nodes are interconnected and influenced by their neighbors. Finally, by structuring the data into graph structure time series datasets, we prepared it for use in machine learning models capable of leveraging both spatial and temporal dependencies. This preparation, often referred to as data pre-processing, is a critical step in any machine learning workflow. It ensures that the input data is in a format that machine learning algorithms can effectively process to learn meaningful patterns and make accurate predictions. Now let's move on to our machine learning architecture. This slide introduces the GNN LSTM architecture. GNN stands for Graph Neural Network and LSTM stands for Long Short-Term Memory, and it takes care of the time series data. So here, this is a hybrid model designed to predict temperature variations along the thermocouple by capturing both spatial and temporal dependencies in the data. The input to this structure is a spatiotemporal temperature data derived from the temperature sensors. The spatial locations along the thermocouple are represented as a graph where each node corresponds to a measurement point and the edges represent spatial relationships between these nodes. Temperature data at each node changes over time, creating a structured time series dataset that serves as the basis for prediction. The forward propagation begins with the graph convolution layer, or you can say the graph neural network part, which processes the graph structure to capture spatial dependencies. This ensures that the model understands how temperature at one location is influenced by its neighbors. The output of the graph convolution layer is then reshaped and passed into the LSTM network, which captures the temporal dependencies in the data This step allows the model to learn how temperature evolves over time at each node. Finally, the processed data is flattened and passed through a fully connected layer, which transforms the learned patterns into specific temperature predictions at the next step. The GNN LSTM architecture offers several advantages. The GNN component captures complex spatial relationships while the LSTM layer effectively models time-dependent trends. This combination creates a highly scalable and robust predictive model that can handle other spatio-temporal datasets beyond battery applications. By accurately predicting temperature variations, this model enables informed decisions to improve battery safety, optimize performance, and prevent thermal events. Here we showcase the results of our machine learning or model that or the architecture that we showed in the previous slide, predicting the temperature along the thermocouple sensor attached to the surface of the faulty battery. The objective here was to demonstrate the capability of the machine learning model to accurately forecast the temperature evolution at specific spatial locations at future time steps. On the left, we see the graph comparing the true temperature values with the predicted values, pink line over time. The model exhibits excellent predictive accuracy as evident by the small root mean square error value of 0.9637. This low RMSE indicates a high degree of agreement between the predicted and actual temperature values, even as the temperature rises rapidly due to thermal runaway. The diagram on the right illustrates the spatial setup where the thermocouple or the thermal sensor spirals along the battery surface. The sensor records temperature data at specific points, and the color-coded gradient along the sensor represents the temperature distribution. Um, the machine learning model predicts the temperature at a specific location marked on the thermocouple. By accurately forecasting this localized temperature, the model provides critical insights into the progression of thermal events, particularly in faulty batteries like B2. This result highlights the effectiveness of the GNN LSTM architecture in learning both spatial dependencies and temporal trends. The accurate prediction empower us to anticipate critical thermal events in advance, offering a pathway towards proactive battery management and enhanced battery safety measures. So let's talk about the work so far in a nutshell, just to provide a summary. So our work combines a multi-physics and machine learning approach to predict thermal runaway in cylindrical lithium-ion batteries and packs, focusing on exothermic side reactions that are the triggering point for thermal runaway. By integrating physics-based model with data-driven methods, we address the critical challenge of thermal safety. For the battery models, spatio-temporal temperature data served as input for the machine learning study. This data set captured both spatial dependencies and time-based trends, enabling our machine learning algorithm to learn patterns of thermal behavior effectively. The machine learning algorithm demonstrated high accuracy during both training and testing, validating its capability to predict temperature and thermal runaway risks. And we believe that our developed framework has the potential to be extended for real-time thermal runaway prediction. This advancement can be a practical solution for enhancing battery safety in optional battery and operational battery systems. So far, we have explored how electrochemical and thermal modeling coupled with AI can predict thermal failures. This is a significant achievement as thermal safety is a top priority in battery systems. However, to implement this framework in real-world battery world applications such as electric vehicles or grid-scale energy storage, we need more than just modeling and predictions. The next step is to focus on an advanced battery management solution. Such a solution bridges the gap between theory and practice, ensuring that battery systems are safe, reliable, and efficient under real-world conditions. Before we dive into the details of our product, the BDPS tool suite, I want to take a moment to discuss in somewhat detail as to why do we even need advanced battery management solutions. As the demand for lithium-ion batteries continues to grow, so does the need for advanced battery management solutions. This is driven by two major trends: the surge in electric vehicle adoptions and the increasing reliance on grid energy storage to support renewable energy. However, managing these batteries comes with significant challenges. Over time, batteries degrade due to repeated charging and discharging cycles, which affects EV range and grid stability. Beyond performance degradation, there are risks of aging-related failures such as thermal runaway, which can be dangerous, or even lithium plating that can happen due to fast charging, especially and additionally, batteries are sensitive to environmental conditions. To tackle these issues, we need predictive insight. Real-time monitoring and forecasting can help prevent unexpected failures, optimize battery lifespan, and ensure efficient operation under varied conditions. The implications of battery degradation are also uh, operational and financial. Frequent battery replacements are unexpected, and unexpected failures drive up maintenance costs, and extending battery life is key to meeting sustainability goals by reducing and conserving resources. This all points to a need for a comprehensive solution that combines data analytics, simulation, and predictive modeling to ensure safe, efficient, and sustainable battery use. That's where the BDPS tool suite comes in. Let's take a deeper look at the BDPS tool suite class of system. As shown in the figures, the BDPS tool suite includes a powerful battery manager designed to enhance both battery performance and lifespan. It uses predictive aging models to anticipate performance degradation under various conditions, identifying specific losses due to charging and discharging. This helps us create operational policies that keep degradation within manageable levels. Running on high performance computing, the suite enables efficient data exchange and user interaction for battery management. Its core battery modeling module factors in battery chemistry and environmental conditions to forecast battery life. Detailed battery profiles covering metrics like capacity, charge, discharge, voltage, and current and temperature are stored to refine our management strategies and ensure optimal performance using the real-time data acquisition interface. The operating conditions module fine-tunes parameters such as charge rate, voltage, and temperature to maintain safety and efficiency even in challenging environments. The BDPS tool suite also includes fault detection and isolation capabilities. By continuously monitoring battery health, it can quickly identify faults and isolate affected cells, helping prevent potential failures before they escalate. This proactive approach to fault management further enhances safety and reliability. We have also have dedicated models for charging and discharging. Our charging models ensure efficient charging processes while the discharging models help reduce wear and extend battery life. The analysis module integrates aging models, dynamically adjusting charge discharge processes and enabling faster charging when conditions allow. The charge and discharge module effectively manages duty cycles, which maximizes energy efficiency, and operation policy is generated to align battery conditions with performance needs, creating a configuration that optimally manages charge rate and voltage to preserve battery health. Lastly, the suite's predictive aging models allow us to forecast performance degradation over time. By adjusting protocols based on variables like charge rate and temperature, we can accurately predict aging and degradation patterns. This ultimately optimizes safety, extends battery life, and enhances performance across a variety of scenarios, including cold weather and fast charging conditions. Thermal modeling plays a pivotal role in the BDPS tool suite by addressing critical aspects of battery safety, performance, and durability. It ensures safety assurance by preventing overheating and thermal failures while enhancing fault detection capabilities. Thermal modeling also contributes to lifespan extension by identifying and mitigating temperature induced degradation, ensuring batteries remain durable over time. Its ability to adapt to extreme conditions like cold weather or high power scenarios makes it essential for real world application. Additionally, real time data integration allows dynamic refinement of management strategies, improving system operations on the fly. The tool suite leverages thermal data to prevent failures by isolating thermal anomalies, preventing cascading effects, and enhancing reliability. It also supports fast charging by balancing rapid charging needs with thermal safety to protect the battery. Finally, thermal modeling improves energy efficiency by minimizing losses and promoting uniform thermal conditions across cells, while also facilitating holistic system integration with other BDPS modules for comprehensive battery health management. Together, these features make thermal modeling a cornerstone of advanced battery management systems. This slide highlights significant value and benefits of the innovation. for the BDPS tool suite. The technology provides a substantial cost advantage compared to traditional empirical data collection methods, reducing lifetime testing time and lowering the cost of battery packs. Additionally, it refines battery management strategies, reducing battery aging, ensuring both cost efficiency and extended battery life. The target market includes electric vehicles, grid energy storage, robotics, and UAVs, with a strong emphasis on maintaining high fidelity knowledge of battery aging to support mission critical planning and completion. Supported by an impressive portfolio of patents and recognized through prestigious awards such as the R&D 100 finalist in 2015 and 2020, this innovation is tailored to meet the needs of the rapidly evolving energy and mobility sectors. This slide emphasizes how we address customer pain points and challenges, and by working closely with industry leaders, researchers, and universities such as DOW Chemical and Dalhousie University. Through these collaborations, we develop tailored solutions to meet specific needs. As an example, one of our products, AEM, that will be later factored in the part of BDPS tool suite, highlights how DOW chemical reduced the number of required electrolyte experiments from 1000 to 300 by leveraging our advanced modeling tools, saving both time and resources. Similarly, for sales cell stage, another tool that is also a part of the BDPS tool suite family. A robotic company utilized our robust physics-based models to optimize battery performance and degradation, improving the efficiency of their charge discharge protocols. These case studies demonstrate how our tools enable customers to streamline processes, enhance battery performance, and reduce operational costs, reinforcing the value of our collaborative approach to solving real-world challenges. Here's a slide for our team. Our team combines expertise in engineering, research, and innovation. Wyatt Pena is the VP of Operations. He has over 8 years of experience in engineering management, cost estimation, and prototype design for CBM, PHM, and IVHM solutions, advancing from intern to key leadership roles at Ridgetop Group. Myself, I'm the senior battery simulation engineer. I have a PhD with over 4 years of experience in electrochemical thermal modeling of batteries. Dr. Kevin Jering, he is a distinguished scientist and a pioneer in molecular-based electrolyte models, invented AEM, cell stage, and other patented technologies with nearly 30 years of R&D experience at Idaho National Lab. Other key team members include data scientists, software engineers, and domain experts, supported by a global sales network spanning North America, South America, Europe, and Asia. This team drives innovation, ensuring excellence in battery modeling and management solutions. So finally, I would like to end with a brief summary. So far, we saw how my research work integrates multi-physics model and AI to predict thermal runaway in lithium-ion batteries. Focusing on side reactions that release exothermic heat release, and that can pose a significant safety risk. By leveraging the spatiotemporal temperature data, we saw that the machine learning algorithm effectively captures spatial dependencies and temporal trends, demonstrating high accuracy in predicting thermal behavior and temperature risk and thermal runaway risk. We also briefly learned about the BDPS tool suite that provides a reliable framework for predicting battery performance and aging, improving design performance and improvement. It also addresses diverse usage conditions in vehicles and grid energy storage, accounting for factors like geography, load patterns, and thermal management. The suite also simulates complex duty cycles, including temperature fluctuations, state of charge, and daily thermal cycling. Additionally, it supports second use application, accessing the viability of repurposed EV batteries for systems like backdrop microgrids or consumer electronics, promoting sustainability and reducing waste. We will talk more in details about BDPS tool suite in our future webinars, so stay tuned. And thank you very much for attending this webinar. And to learn more about our products, please visit our website or LinkedIn page for more detailed information, and feel free to reach out to us. We'd be delighted to connect, and we are always open to collaboration and new opportunities. Thank you.